Let's have a look at the expression for Hooke's law. It says that the force of a spring is equals to k times the elongation x. If that is the only force on the spring, we can apply Newton's second law and find the acceleration. In this case, we would have the spring oscillating back and forth. But because the acceleration is the derivative with respect to time of the derivative with respect to time of the position, we get this differential equation. A differential equation is an equation that contains a function, in this case the position, and its derivatives. This equation tells us that if we derive twice with respect to time the position of the extreme of the spring, we obtain again an expression that is proportional to the position. The solution for this differential equation is a trigonometric function, either the sine function or the cosine function. Let's consider the position as a times the cosine of a constant omega times t. This omega is the angular frequency of the oscillations. If we derive this function, we obtain that the velocity is negative omega times a times the sine of omega t. If we derive again, we obtain that the velocity is the negative omega squared times a times the cosine of omega t. Comparing this last equation with the first one for the Newton's second law, we see that this omega is equal to the square root of k divided by the mass.